Hello, and welcome. Today I want to take you to the true frontier of scientific investigation. What if I told you that there are 4 major challenges facing astronomy in the 21st century that are redefining what it means to understand the universe? We have reached a point where the questions have become greater than the certainties we have accumulated. For billions of years, the cosmos has evolved under influences that have not yet been fully identified, even with the remarkable precision of modern instruments. Imagine mastering sophisticated calculations and still realizing that the central pillars of our explanations remain incomplete. Why is it that the limits have become so apparent precisely now? Throughout this long journey, we will explore how these 4 great challenges intersect with the expansion of space, the dominant presence of invisible matter and energy, the ongoing influence of extreme particles, and the very real obstacles of exploration beyond Earth, forming a single narrative about the current state of astronomy. But before we continue, I need your help. Leave a like, subscribe so you don't miss future videos, and share this story. Cosmos for Rest depends on your support, and it truly helps us keep going. Now, relax, close your eyes, and let science guide you. To begin this journey across the frontier of knowledge, we must first accept that our old way of understanding the heavens has quietly been left behind. What we are experiencing now at the beginning of the 21st century is a transformation so profound that it changes not only what we understand, but the very nature of our role as observers of time and space. You would hardly believe it if I told you that throughout our entire history, we have been focused on nothing more than a thin layer of foam floating atop an ocean of invisible mysteries. The journey from classical astronomy to frontier astronomy is the story of how our species came to realize that vision, no matter how sophisticated it has become, is only one of many senses required to understand the true structure of reality. Imagine the earliest astronomers, men and women who relied only on patience and geometry to predict the motion of the planets. To them, the cosmos was a mechanism of precision, a predictable dance of spheres governed by understandable and orderly mechanical laws. When the first magnifying instruments arrived a little more than 4 centuries ago, lenses allowed us to reach details that had once been impossible to see, yet the paradigm remained unchanged. To understand was to observe light. However, as we moved into this new century, that certainty began to dissolve. We discovered that the universe is not merely a place filled with bright objects floating through emptiness, but a dynamic, vibrant fabric that is, for the most part, completely hidden from our biological senses. Contemporary astronomy is no longer satisfied with simply recording the glow of stars. It must feel the pressure of gravity, capture ghost-like particles, and interpret signals that travel across space without emitting a single trace of visible light. This turning point where we now stand is what we call the era of multi-messenger astronomy. It is as if, after spending our entire existence watching a silent play, we suddenly gained hearing, touch, and the ability to sense heat. The 21st century has introduced us to a cosmos that speaks through waves, neutrinos, and particles carrying unimaginable energies. And this is where the 4 challenges we are about to explore become our new compass. We have stepped beyond the comfort of direct measurement and entered the realm of deep inference. When we turn our attention to the sky today, we are not searching only for light. We are searching for evidence of an architecture that refuses to reveal itself in a simple way. Can you imagine the complexity of operating detectors that do not point toward the stars, but instead toward the interior of Earth or the depths of eternal ice, searching for signals that pass through entire planets without encountering resistance? The transition to this new way of doing science has brought with it a necessary humility. Throughout the 20th century, we accumulated data at an unprecedented pace, but now those data are beginning to reveal gaps that our established theories cannot fully explain. The challenge is no longer merely technical in the sense of building larger instruments. It is a challenge of interpreting reality itself. We are trying to understand how human life can endure during long-duration space travel, while, at the same time, attempting to decipher what the very space we intend to travel through is actually made of. It is a dual pursuit. outward toward the vastness and inward toward the fundamental laws of matter. This duality defines the spirit of our age, where every new discovery brings 10 new questions that challenge answers we once considered definitive. The first major pillar of this new era is the recognition that our physical presence in the universe is fragile and constrained by biological laws that evolved under the protective embrace of our planet. When we think about these 4 challenges, the first one strikes directly at our identity as explorers. Leaving our natural protection is not merely a matter of propulsion or speed. It is a direct confrontation with the physics of high-energy particles and with the absence of a force that shaped every bone and every fiber of our being over millions of years. Astronomy has merged with biology in a way we never anticipated. It is no longer enough to understand the surface of distant worlds. We must understand whether our own molecular structure can survive a journey under the relentless bombardment of radiation that no technology we possess today can completely stop. At the same time that we look toward our survival, we are confronted by the monumental scale of what we cannot see. The transition into modern astronomy revealed that everything we know, from spiral galaxies to colorful nebulae, accounts for less than 5% of the total density of the universe. That means 95% of the cosmos consists of something we call dark matter and dark energy. You would hardly believe that the entire history of science has been written based on only a tiny fraction of reality. This is the era in which we have chosen to face that invisible giant. We are no longer satisfied with watching stars move. We want to understand the hidden mass that holds them together and the mysterious force pushing galaxies farther and farther apart. This shift in perspective requires messengers that challenge the imagination. To capture neutrinos, for example, we do not use mirrors, but enormous tanks of ultra-pure water or cubic kilometers of polar ice, waiting for a subtle signal that reveals the passage of a particle that has traveled for billions of years without being deflected by anything. This is the essence of modern astronomy, using messengers other than light to tell stories about events that light itself cannot show us. Neutrinos can emerge from the heart of a collapsing star or from the surroundings of a black hole, carrying information about physical processes that occur in environments so dense and so hot that no conventional lens could ever record them. We have learned that if we wish to understand the universe, we must be willing to listen to its silence and capture its most discrete particles. Frontier astronomy also places us face to face with the mystery of cosmic rays, charged particles that strike our atmosphere, carrying energies millions of times greater than anything we can produce in the largest particle accelerators ever built by human hands. The challenge here is one of origin and mechanism. Where do these natural cannons come from? What kind of cosmic object can accelerate a single atom to a speed so close to light that it carries such extraordinary energy? The 21st century forces us to understand the sky as a laboratory of extreme energies, where nature's most violent events leave traces that we struggle to follow, despite magnetic fields that bend their paths and turn the search for their source into a true investigation across the void. We are therefore living through a moment of synthesis. Astronomy is no longer an isolated discipline, but a meeting point between physics, biology, and materials engineering. The 4 challenges we will explore throughout this journey are not merely problems waiting to be solved. They are the outlines of the map we are drawing for future generations. Each of these challenges represents a frontier where our current knowledge ends and our curiosity begins to reach into the unknown. It is an age of great questions, where humility before the vastness is joined by the audacity to try to understand it. And as we prepare to dive into the details of each of these frontiers, it is important to remember that we are the first generation of human beings fully aware of the depth of our own ignorance about the cosmos. In the 21st century, astronomy has become an intimate conversation with the invisible. We no longer seek only the beauty of space photography, but the hidden truth contained in data from sensors capable of detecting the slightest variations. With every step we take toward solving these 4 challenges, we realize that the universe is far stranger, far larger, and far more interconnected than any astronomer of the past could have imagined. Where we once saw only fixed points of light, we now perceive streams of particles, currents of invisible forces, and the traces of events that shape the destiny of everything that exists. It is within this landscape of transition that our journey truly begins, inviting each of you to feel the weight of inhabiting a cosmos that has finally begun to reveal its deepest and most challenging secrets. To understand the first of these challenges, we must first understand what happens when our own bodies cease to be earthbound observers and become passengers of deep space. Frontier astronomy begins in the skin of the explorer and in the nucleus of every cell, because there is no conquest of the universe without the preservation of life. If we hope to reach the mysteries of matter or the sources of extreme particles, we must first overcome the physical and biological barriers that space imposes. This is the starting point: human fragility standing before the radiant, weightless immensity that awaits beyond our protective atmosphere. The 21st century teaches us that the sky is not merely something to be observed, but an environment that constantly tests the organized matter that we are. Can you imagine what it would be like to spend months or even years in an environment where every ray of light carries the potential to alter your own genetic code? The challenge of long-duration space travel is the ultimate proof that astronomy now requires us to understand life as deeply as we understand planetary orbits. Space radiation, microgravity, and isolation are not merely technical obstacles. They are physical frontiers that define how far our species can truly go. And it is this first great barrier, the challenge of keeping life functional within the abyss, that we must examine if we are to understand how humanity intends to finally leave Earth's cradle and venture into the unknown. To deepen our understanding of where contemporary astronomy is heading, we must confront the most intimate and perhaps most unsettling reality of exploration: our own biological fragility in the face of the abyss. You would hardly believe it if I told you that the greatest obstacle standing between us and the stars is not the power of our engines or the sophistication of our computers, but the delicate structure of our cells. When we leave the protective embrace of Earth, we enter a domain where physics and biology engage in a silent and relentless struggle. Leaving our atmosphere is not simply a change of scenery. It is the abandonment of the magnetosphere, that invisible shield that protected us for billions of years against the constant bombardment of the sun and the depths of the galaxy. Without that protection, long-duration spaceflight becomes a challenge of survival at the molecular level, where every second of the journey represents a confrontation with particles traveling at speeds approaching that of light. Imagine existing in an environment where the danger is completely invisible, odorless, and silent, yet capable of passing through the steel walls of a spacecraft as if they were smoke. Space radiation is not an abstract concept. It consists of particles carrying extraordinary amounts of energy, such as solar protons and galactic cosmic rays. Can you imagine the subconscious awareness that your own genetic code is under continuous bombardment? Beyond Earth's magnetosphere, the flow of these particles is constant. A galactic cosmic ray is, in essence, the nucleus of an atom accelerated by violent events elsewhere in the galaxy, carrying an impact force that defies intuition. When these particles strike the body of an explorer, they do not simply cause superficial damage. They pass through tissues and reach deoxyribonucleic acid, the strands that carry the instructions of life, creating breaks that the body is often unable to repair perfectly. This may sound unbelievable, but the protective engineering we rely on here on Earth is almost useless in deep space. On our planet, the thick atmosphere and magnetic field deflect and absorb most of this energy. In space, the obvious solution would seem to be thicker shielding, perhaps using heavy metals such as lead. Yet physics presents us with a cruel irony. When a high-energy particle strikes a dense shield, it can fragment, producing what we call secondary radiation. Instead of stopping a single particle, the collision generates a cascade of smaller particles that are just as dangerous and spread throughout the spacecraft. It is as though, in trying to build a wall against a bullet, the wall itself explodes into deadly fragments. This engineering limitation defines the maximum safe duration of any mission. It is not merely a matter of carrying enough food or oxygen. It is a biological countdown imposed by particle physics. You may be wondering how astronomy deals with such a concrete reality. The truth is that the exploration of the solar system and the establishment of inhabited observatories on other worlds depend entirely on solving this equation. The risks of cancer, neurological damage, and cardiovascular changes are real consequences that transform the dream of colonization into a rigorous assessment of risk. Secondary radiation forces us to seek alternative materials, such as hydrogen-rich polymers, or even water reservoirs used as shields, because hydrogen is more effective at absorbing the impact of heavy nuclei without creating atomic fragments. Notice how humility becomes essential in science. Before we can observe distant galaxies from a lunar or Martian base, we must first ensure that the human brain, the instrument interpreting those observations, is not degraded by the environment in which it exists. Beyond the invisible assault of particles, life in the void demands a confrontation with the absence of a force we have taken for granted since the first second of our existence: gravity. Can you imagine what happens to an organism that evolved for millions of years under constant pressure when that pressure suddenly disappears? In microgravity, the human body begins a silent and troubling transformation. Without the need to support its own weight against Earth's pull, the skeletal system starts losing bone mass at an alarming rate, shedding calcium as though bones were no longer necessary. Muscles, including the heart, begin to atrophy because the effort required to move blood and limbs is dramatically reduced. What appears to be graceful floating in orbital videos is actually a state of profound physiological stress, where bodily fluids shift upward, altering intracranial pressure and affecting astronauts' vision. These changes in fluid distribution and the loss of mineral density are not merely inconveniences. They are factors that limit human autonomy in space. If we intend to carry out missions lasting years, such as a round-trip journey to Mars, we must learn how to mitigate these effects through intense exercise, advanced pharmaceuticals, and perhaps the development of artificial gravity through rotation. Yet every one of these solutions introduces new engineering and logistical challenges. 21st century astronomy is therefore inseparably connected to space medicine. The observer cannot be separated from the environment being observed. This biological challenge is the first major filter that will determine whether we remain a species confined to a single planet or become capable of inhabiting the cosmic ocean in a sustainable way. It is both fascinating and sobering to recognize that the isolation of a space mission also exacts a price from the human mind. Imagine living inside a sealed habitat where communication with Earth may experience delays of up to 20 minutes each way, depending on distance. That forced silence, that awareness of being inside a tiny lifeboat surrounded by lethal vacuum, requires a psychological resilience possessed by very few people. Life support logistics, the endless recycling of air and water, and the need for absolute redundancy transform daily life into a continuous exercise in vigilance. In the 21st century, we understand that the greatest threat to a long-duration astronomical mission may be a simple human error caused by fatigue or prolonged social isolation. Modern astronomy, therefore, is not built solely on calculations of stellar orbits, but also on protocols governing human behavior under extreme conditions. Every robotic mission we send today acts as a scout, measuring radiation levels and testing material durability so that human presence may one day become possible. Can you see how much deeper this reality is than science fiction often portrays? This is not a romantic adventure. It is a biological struggle against the laws of thermodynamics and electromagnetism. The exploration of the solar system and the maintenance of major space observatories require us to solve this entire package of problems: biology, radiation, engineering, and time. Space radiation, in particular, remains the most difficult puzzle. While the Sun follows cycles of activity with eruptions that can be monitored and, to some degree, predicted, galactic cosmic rays are unpredictable and ever-present. They are unwanted messages from distant supernovas and active black holes, particles that have crossed the void for ages, only to encounter our technology and our flesh. Multi-messenger astronomy, which uses these same particles to understand the universe, is the very science that must also find ways to protect us from them. There is both a poetic and technical duality here. The same particle that brings news of a star that died 1,000,000 years ago is also the particle that threatens the health of the explorer attempting to study it. Understanding this gives us a renewed respect for Earth. Our planet is not merely a launch platform, it is a unique biological sanctuary where the magnetosphere and atmosphere form a life support system that we can barely imitate with our most advanced spacecraft. The challenge of long-duration travel proves that we are terrestrial beings trying to learn the language of an environment that was never designed for us. Yet it is precisely this challenge that drives innovation. In our efforts to shield the human body from space radiation, we develop new materials and new genetic therapies that also benefit life here on Earth. The quest to inhabit the void teaches us about our own molecular nature. As we reflect on these biological difficulties, we begin to realize that 21st century astronomy is a science of limits. We are testing how far organized life can travel before it begins to break down under the weight of universal physical laws. This first frontier, the frontier of flesh, is what gives meaning to the scientific effort. We are not merely machines processing data. We are carbon-based beings seeking to understand a universe of radiation, invisible forces, and matter unlike ourselves. And as we learn to protect our fragile bodies, we earn the right to look deeper into the abyss, searching for answers to questions that extend far beyond our own survival. Feel the scale of this challenge. Every centimeter of shielding aboard a spacecraft is a negotiation with the cosmos. Every minute of exercise in microgravity is a declaration of resistance against entropy. And every piece of data collected about the effects of radiation on the human brain is another step toward an astronomy that does not merely observe reality, but actively participates in it. The 21st century invites us to become more than spectators. It challenges us to become conscious inhabitants of the vastness, accepting our fragility and building our greatness upon it. This understanding of human limits prepares us for the next stage of our journey. If the body faces challenges in crossing space, the mind faces even greater mysteries when it tries to explain what space itself is made of. After understanding the struggle of life in the void, we must now descend into the mystery of the invisible architecture that holds galaxies together and accelerates the expansion of everything we know. Having confronted the reality of flesh, frontier astronomy now turns toward the colossal shadows we call dark matter and dark energy, the components that truly govern the destiny of the universe. To understand how humanity intends to inhabit the silence between worlds, we must examine the invisible mechanisms that sustain life when nothing but metal and technology stand between us and absolute vacuum. You would hardly believe the psychological and logistical complexity involved in the simple act of remaining functional millions of miles from any solid ground. If we have already explored the assault of radiation and the transformation of bones in microgravity, we must now understand the strategy behind endurance itself. 21st century astronomy is not limited to observing distant objects. It is about creating life support systems so refined that they become closed circles of existence. Imagine living in an environment where every molecule of oxygen you breathe has already passed through your lungs thousands of times, purified and returned by machines that can never be allowed to fail. This endless recycling is the foundation of long-duration space logistics, transforming the spacecraft into an artificial organism where nothing is wasted and everything is transformed to ensure the continuity of human life. Maintaining these life support systems requires a level of technical discipline that borders on the sacred. Can you imagine knowing that the water you drink today is the result of carefully processing every trace of vapor, sweat, and waste produced by both the crew and the habitat over previous weeks? This circular economy is not merely a matter of reducing weight. It is the only viable strategy for missions lasting hundreds of days, where resupply from Earth becomes physically impossible. Every drop of fluid becomes a precious resource, moving through resin filters, reverse osmosis membranes, and thermal distillation systems in a cycle that mirrors, on a tiny scale, what our planet accomplishes through its oceans and atmosphere. Exploration astronomy requires us to become masters of managing finite resources, learning to value every carbon atom and every hydrogen particle as though they were the rarest treasures in the galaxy. Yet beyond the mechanics of fluids and gases lies a much more subtle and dangerous force acting upon the explorer, the psychology of isolation. Imagine what it means for the human mind to realize that its entire world consists of only a handful of pressurized rooms surrounded by endless darkness. This may sound astonishing, but prolonged confinement alters our perception of both time and space. Without the natural cycle of day and night provided by Earth's rotation, the brain depends on carefully programmed artificial lighting to preserve its circadian rhythm and prevent sleep and mood from deteriorating. Social isolation, limited to a tiny group of companions, demands emotional intelligence and conflict resolution skills that are just as critical as expertise in astrophysics. In the 21st century, we recognize that one of the greatest threats to a mission to Mars or the operation of a lunar observatory may be the gradual erosion of mental health caused by homesickness, monotony, and the constant awareness of one's own vulnerability. One of the most unsettling aspects of this experience is the delay in communication, a purely physical phenomenon that creates an unavoidable barrier to human connection. As a spacecraft moves farther away from Earth, messages traveling at the speed of light take increasingly longer to reach their destination. Can you imagine trying to maintain a conversation with your family when every question takes 20 minutes to arrive and every answer takes another 20 minutes to return? This gap in time breaks the natural flow of dialogue and reinforces the feeling that you are living in a different reality from the rest of humanity. For astronomy, this delay means that crews must operate with unprecedented autonomy. There is no possibility of waiting for instructions from mission control during an immediate emergency. The explorer must possess both the technical expertise and the emotional composure to make critical decisions in a matter of seconds, knowing that support from Earth is little more than a distant echo from the past. This strategy of complete autonomy requires spacecraft systems to be designed with absolute redundancy. On Earth, when equipment fails, we simply replace a part. In deep space, you must either repair what you have or manufacture a replacement using advanced three-dimensional fabrication technologies. 21st century logistics has transformed spacecraft into miniature factories, capable of turning raw materials into precision components. Yet the most important redundancy remains human. Every crew member must be able to perform multiple roles. An engineer must understand medicine. A biologist must be capable of celestial navigation. A pilot must know how to operate complex life support systems. This integration of knowledge is what makes it possible to confront the challenge of distance. Astronomy has evolved from the effort of isolated specialists into a perfect partnership between human beings and machines, where the survival of each depends on the shared expertise of all. You would hardly believe the pressure that silence itself places on the senses. During a long-duration mission, there is no sound of wind, no scent of rain on the ground, and no changing colors of the seasons. This sensory deprivation can lead to lethargy or hypersensitivity, where even the smallest mechanical noise inside the spacecraft is interpreted as a threat. To counter this, modern strategies include virtual reality environments that allow the mind to briefly escape into forests, beaches, and familiar landscapes. Yet these are only temporary remedies against the physical reality of confinement. Astronomy teaches us that if we wish to conquer the universe, we must first conquer our own dependence on natural stimulation, adapting our consciousness to an environment of absolute austerity and unwavering technical focus. Another fundamental aspect of this journey is the management of risk and failure. During long-duration missions, the concept of zero error ceases to be an aspiration and becomes a condition for survival. The maintenance of systems responsible for removing carbon dioxide from the air, for example, is a daily task requiring extraordinary precision. If those purification systems fail and backup mechanisms do not activate immediately, the crew can face suffocation within a relatively short period of time. Frontier astronomy is therefore a science of vigilance. The explorer lives in a state of continuous awareness, constantly monitoring diagnostic displays and listening for warning signals from the spacecraft. Maintaining this level of alertness for months at a time consumes enormous mental energy, forcing us to develop methods of rest and recovery that are every bit as sophisticated as our propulsion systems. The connection between these human challenges and astronomical goals is both direct and profound. We cannot build and maintain radio telescopes on the far side of the Moon or optical observatories at distant Lagrange points unless we are capable of keeping human hands there to operate and repair them. Robots can accomplish a great deal, but human presence provides a flexibility and capacity for discovery that no current artificial intelligence can fully replicate. The human eye, trained to recognize patterns, and the human mind, capable of intuitive leaps, remain the ultimate observational instruments. But for those instruments to function, the supporting systems must be flawless. Logistics and psychology have therefore become some of the most important supporting disciplines of 21st century astronomy. Imagine the complexity of planning nutrition for a journey lasting 1,000 days. The challenge is not merely providing enough calories, but preserving the enjoyment of eating in order to sustain morale. Growing fresh food through hydroponics inside small space greenhouses is one of the most promising solutions. Beyond supplying essential vitamins, contact with living plants and the act of cultivating life in the middle of the cosmic desert provide remarkable psychological benefits. Watching a seed sprout in an environment without soil and beneath artificial light is a powerful reminder of our connection to life on Earth. Space agriculture represents the bridge between our origins as hunter-gatherers and our future as interplanetary travelers. It is fascinating to realize that, in order to understand the most distant galaxies, we first need to learn how to grow lettuce in the vacuum of space. Therefore, the challenge of long-duration space travel is a test of endurance for our civilization. It forces us to view technology not as an end in itself, but as an extension of our skin and our organs. A spacecraft is not simply a vehicle. It is a colossal life support prosthesis. Every bolt, every water filter, and every line of code running through the onboard computer serves as a strategy for protection against the void. As we refine these mechanisms, we become increasingly capable of carrying our curiosity beyond its current boundaries. Modern astronomy is, ultimately, the art of making the inhospitable habitable, allowing the light of consciousness to continue shining even in the darkest and most silent regions of the solar system. Now feel the weight of that responsibility. Every decision made in the design of a space habitat is a promise of safety to those who will dare to cross the void. The same science that studies the stars must also study, with equal dedication, the heartbeat of a solitary astronaut. In the 21st century, we have come to understand that the cosmos is not merely a place to be observed, but a challenge to be lived. To overcome that challenge, we require a perfect harmony between the precision of technical data and the resilience of the human spirit. Only when we master the art of living within the abyss will we possess the authority to unravel the secrets the abyss itself conceals. With this foundation of survival established, we are ready to set aside the fragility of flesh and focus on mysteries that transcend our immediate physical perception. If logistics allows us to cross space, it is imagination and calculation that allow us to perceive what space itself conceals. Our journey now moves beyond the visible and into the shadows that govern the motion of stars and shape the structure of galaxies. We now turn our attention to the mystery of dark matter, the invisible substance that holds the universe together, while challenging everything we thought we understood about mass and light. Now that we understand the barriers imposed by our own biology, we must look outward with a level of honesty that is almost unsettling. You would hardly believe it if I told you that everything we have explored so far, every star we have mapped, every galaxy we have photographed, and every grain of cosmic dust we have analyzed represents only a small island of light within a vast and absolute ocean of darkness. The greatest secret of 21st century astronomy is that we are essentially blind to most of reality. The universe we can see is only the tip of a monumental iceberg. We are now entering the domain of the invisible, where dark matter and dark energy govern the fate of everything that exists without ever having emitted a single photon that our instruments could directly capture. Imagine the frustration and the fascination of realizing that 95% of the cosmos consists of something we do not know, yet whose presence we feel through its gravitational influence and its effect on cosmic expansion. To begin understanding this mystery, we must turn our attention to the way galaxies move. Can you imagine a carousel spinning so quickly that every child riding it should be thrown outward by centrifugal force, yet somehow they remain firmly in their seats? That is precisely what astronomers discovered when they observed the rotation of spiral galaxies. According to the laws of physics established by Isaac Newton and Albert Einstein, stars located on the outer edges of a galaxy should orbit much more slowly than those closer to the center, because there is less visible mass exerting gravitational influence upon them. Yet observations revealed something deeply unsettling. Distant stars move at nearly the same speed as those near the galactic core. They are traveling so fast that the galaxy should simply tear itself apart, scattering its stars into the void. The fact that it remains intact is evidence that there is an enormous amount of unseen mass present, a form of dark matter acting as an invisible gravitational glue, holding the entire galactic structure together. This discovery, driven in large part by the pioneering work of Vera Rubin, permanently changed our understanding of cosmic architecture. You would hardly believe the scale of this gravitational phantom. We are not dealing with a minor calculation error, but with a discrepancy so large that it suggests there is roughly 5 times more invisible matter than ordinary matter. Dark matter is not composed of atoms, protons, or electrons like the matter that makes up our bodies and our world. If it were, it would interact with light by absorbing or reflecting it. Instead, it appears to be something fundamentally different, a substance that passes through our bodies, our homes, and our planet at this very moment without producing any sensation at all. It reveals itself only through gravity. It is as though we were trying to understand the rules of a chess game while seeing only the white pieces move, unaware that the invisible black pieces are controlling the entire flow of play. One of the greatest challenges of modern astronomy is discovering what this mysterious substance is that supports the structure of every galaxy we know. But the secrets of the invisible do not end there. There is an even deeper and more energetic mystery that permeates all of space: dark energy. To understand the impact of this discovery, imagine throwing a baseball into the air. Intuition and gravity tell us that the ball should rise, slow down, and eventually fall back. In the cosmos, we expected the expansion of the universe, which began at the dawn of time, to gradually slow as the gravitational attraction between galaxies pulled everything together. Yet, at the end of the 20th century, observations of distant supernovas left scientists astonished. The universe is not slowing down. Quite the opposite. It is expanding faster and faster. It is as if the baseball you threw upward suddenly ignited a rocket engine and accelerated toward infinity. This mysterious influence that drives the very fabric of space-time apart is what we call dark energy. Dark energy is perhaps the strangest element in all of modern physics. It is not concentrated inside objects. Instead, it appears to be a property of space itself. Can you imagine a form of nothingness that possesses energy? As the universe expands, more space comes into existence. And if dark energy is truly an intrinsic property of space, then the total amount of this energy also increases. This idea challenges some of our deepest intuitions about conservation and reality. The empty vacuum that once seemed like a passive backdrop may actually be one of the most powerful influences shaping the destiny of the cosmos. What makes this challenge even more profound is that we still do not know exactly what dark energy is. It may be related to the cosmological constant proposed by Albert Einstein. It may be evidence of an unknown field permeating all of existence. It may even suggest that our understanding of gravity itself is incomplete. Whatever the answer turns out to be, it forces us to confront a humbling possibility. The framework we currently use to describe the universe may be missing one of its most important pieces. Imagine attempting to understand the workings of an entire city while being able to see only a few streets illuminated at night. That is our current situation. The stars, planets, nebulae, and galaxies we observe are merely the visible districts of a much larger reality. Dark matter provides the hidden structure. Dark energy shapes the overall evolution. Together, they dominate the cosmic budget, while everything familiar to us represents only a tiny fraction of the whole. The evidence for dark matter extends far beyond the rotation of galaxies. Astronomers have observed massive clusters of galaxies bending light through a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, mass warps space-time, causing light to follow curved paths. When researchers measure the amount of visible matter within these clusters, they consistently find that there is far too little mass to account for the observed distortion. Something unseen is contributing additional gravity. Once again, dark matter emerges as the most compelling explanation. These observations allow astronomers to create maps of invisible structures stretching across vast cosmic distances. Remarkably, the dark matter appears to form a gigantic framework upon which galaxies assemble. The visible universe may be compared to dew collecting along an enormous cosmic web. We see the droplets, but the underlying structure supporting them remains hidden from direct view. This realization transformed astronomy from a science of luminous objects into a science of unseen architecture. Yet despite decades of effort, dark matter has never been directly detected in a laboratory. Around the world, scientists have constructed highly sensitive detectors deep underground, shielded from ordinary sources of interference. These experiments search for rare interactions between dark matter particles and ordinary matter. So far, the results have remained elusive. The invisible scaffolding of the cosmos continues to evade capture. This uncertainty has inspired alternative ideas. Some researchers have proposed that dark matter may not exist at all, and that the true solution lies in modifying our understanding of gravity. According to these proposals, the laws governing motion on enormous cosmic scales may differ from the laws we observe locally. While these theories remain controversial, they illustrate the depth of the mystery. We are not simply debating details. We are questioning the foundations of how the universe operates. The challenge posed by dark matter and dark energy is therefore much larger than identifying two unknown ingredients. It is a challenge to our entire understanding of reality. Every observation forces us to ask whether we are missing new particles, new fields, new laws, or perhaps an entirely new way of thinking about space and time. The universe continues to reveal that it is under no obligation to conform to our expectations. As we look deeper into the cosmos, we find ourselves in a remarkable position. We possess extraordinary instruments capable of observing galaxies billions of light years away. We can measure subtle fluctuations in ancient radiation left over from the early universe. We can trace the motions of stars with astonishing precision. Yet the dominant components of the cosmos remain hidden. Knowledge has expanded dramatically, but so has our awareness of what we do not know. This is one of the defining characteristics of frontier astronomy. The farther we advance, the larger the unknown becomes. Each answer opens new questions. Each discovery reveals deeper layers of complexity. And nowhere is that reality more evident than in our struggle to understand the invisible forces that shape the universe itself. Yet dark matter and dark energy are not the only invisible messengers challenging our understanding of the cosmos. The universe also communicates through particles carrying energy so extreme that they stretch the limits of known physics. To understand the next great challenge facing modern astronomy, we must turn our attention to cosmic rays, some of the most energetic particles ever observed in nature. Imagine a single atomic nucleus accelerated to a speed so close to that of light that it carries millions of times more energy than the particles produced inside humanity's largest accelerators. This is not science fiction. These particles constantly strike Earth's atmosphere, arriving from distant regions of the universe with energies that continue to astonish researchers. The challenge is deceptively simple to state. Where do they come from? You would hardly believe how difficult it is to answer such a question. Cosmic rays do not travel through empty space in straight lines. Because they are electrically charged, they interact with magnetic fields scattered throughout galaxies and intergalactic space. By the time they reach Earth, their paths have been bent and twisted countless times. It is as if investigators discovered a trail of footprints leading to a crime scene, only to realize that every step had been scrambled by a storm. The particle arrives, but its origin remains hidden. This transforms the search into one of the most demanding detective stories in modern science. Researchers suspect that some cosmic rays originate from exploding stars known as supernovas. Others may come from the surroundings of supermassive black holes, where matter falls inward while enormous amounts of energy are released. Some may even be accelerated within powerful jets, emerging from active galaxies billions of light-years away. Each possibility represents an environment far more extreme than anything we can reproduce on Earth. The remarkable reality is that the universe functions as a natural particle accelerator on a scale beyond human imagination. While our most advanced facilities require immense engineering efforts to accelerate particles over many miles, nature accomplishes similar feats using magnetic fields, shock waves, and gravitational forces operating across entire star systems and galaxies. Every high-energy cosmic ray arriving at Earth carries information about processes occurring in these extraordinary environments. Yet information alone is not enough. We must learn how to interpret it. When a cosmic ray collides with Earth's atmosphere, it triggers a cascade of secondary particles that spread outward over enormous areas. Instead of detecting the original particle directly, astronomers often measure the shower of particles produced by its impact. Sophisticated observatories covering vast stretches of land monitor these events, reconstructing the properties of the original visitor through the traces it leaves behind. Can you imagine the precision required for such work? Scientists are attempting to identify the source of a particle that may have traveled for millions of years across interstellar space, carrying only the faintest clues about its birthplace. Every measurement becomes a puzzle. Every detection becomes a fragment of a much larger story. The study of cosmic rays also connects directly to the broader framework of multi-messenger astronomy. These particles do not exist in isolation. They are linked to neutrinos, gravitational waves, gamma rays, and other signals emerging from the universe's most violent phenomena. By combining these different messengers, astronomers can construct a more complete picture of events that would otherwise remain hidden. Imagine witnessing a distant cosmic catastrophe through several senses at once. One messenger reveals the energy involved, another reveals the motion of matter, another exposes conditions deep within the source itself. Together, they provide a level of understanding that no single observation could achieve. This is why multi-messenger astronomy has become one of the defining revolutions of the 21st century. The challenge, however, extends beyond detection. It also reaches into fundamental physics. Some cosmic rays carry energy so enormous that they test theories developed under laboratory conditions. They allow us to study nature in regimes that cannot be reproduced by human technology. In a sense, the universe conducts experiments for us, offering glimpses of physical processes operating under conditions far beyond our direct reach. Every time one of these particles reaches Earth, it brings with it a message from an environment of extraordinary violence and power. It may have begun its journey near a black hole. It may have been launched by a collapsing star. It may have traveled across distances so immense that entire civilizations could rise and fall during its voyage. And yet it arrives here, colliding with our atmosphere and providing a fleeting opportunity to learn something new about the cosmos. This challenge reminds us that astronomy is no longer limited to observing distant objects through telescopes. We are studying particles that physically arrive at our planet after crossing unimaginable distances. We are transforming Earth itself into a detector, using the atmosphere, ice sheets, underground laboratories, and giant observatories as instruments for understanding the universe. As our ability to interpret these messengers improves, we move closer to answering some of the deepest questions in astrophysics. What mechanisms generate such extreme energies? Which cosmic environments are responsible? How do these processes influence the evolution of galaxies and the larger structure of the universe? These questions remain open, but every new observation brings us closer to understanding the answers. The study of cosmic rays represents another frontier where certainty gives way to mystery. We know these particles exist. We know they carry extraordinary energies. We know they originate beyond our planet. Yet the full story of their creation remains hidden. Like dark matter and dark energy, they remind us that the universe still contains secrets far beyond the reach of our current understanding. We have now arrived at a remarkable point in our journey. After confronting the biological limits of exploration, the hidden architecture of dark matter and dark energy, and the extreme particles that carry messages from the most violent regions of the cosmos, we can begin to see the broader picture taking shape. The four great challenges of 21st century astronomy are not isolated problems. They are deeply connected pieces of a much larger story about humanity's attempt to understand its place within the universe. What makes this era so extraordinary is not merely the sophistication of our instruments, but the realization that every answer seems to reveal a deeper layer of mystery. We have learned that survival beyond Earth is far more difficult than early generations imagined. We have discovered that most of the universe consists of components we cannot directly observe. We have found that nature accelerates particles to energies beyond anything our technology can currently achieve. And through all of this, we have come to understand that knowledge is not a destination, but a horizon that continues to move farther away as we approach it. You would hardly believe how dramatically our perspective has changed in just a few generations. Not long ago, astronomy was primarily concerned with mapping stars, measuring planetary motions, and cataloging visible objects. Today, it has become a discipline that investigates invisible matter, hidden energy, gravitational distortions, subatomic particles, biological adaptation, advanced engineering, and the fundamental nature of reality itself. The boundaries that once separated scientific fields have begun to dissolve. Astronomy has become a meeting place where physics, biology, chemistry, engineering, and mathematics converge in pursuit of the same questions. Perhaps the most profound lesson of all is the value of humility. The more we learn about the universe, the more clearly we recognize how much remains unknown. This is not a sign of failure. Quite the opposite. It is evidence that science is functioning exactly as it should. Every mystery uncovered becomes an invitation to explore further. Every unanswered question becomes a doorway leading toward deeper understanding. Can you imagine what future generations may discover? They may identify the true nature of dark matter. They may determine whether dark energy is a property of space itself or evidence of entirely new physics. They may learn how to shield human beings from the hazards of deep space and establish permanent communities beyond Earth. They may uncover the origins of the highest energy particles in the universe. Some of the questions that seem almost impossible today may one day become fundamental knowledge taught in classrooms. And yet, even if those mysteries are solved, new mysteries will emerge. That is the nature of scientific exploration. The universe is not a puzzle with a final piece waiting to be placed. It is an endless landscape of discovery where every summit reveals another horizon beyond it. The deeper we look, the more expansive reality becomes. This is why astronomy remains one of humanity's most powerful intellectual adventures. It invites us to think beyond the limits of daily life. It encourages us to measure our existence against scales of space and time so vast that they challenge the imagination itself. It reminds us that we are part of a story far larger than our individual lives, a story written across billions of years and countless galaxies. The four challenges we have explored are therefore more than scientific problems. They are symbols of our species' enduring curiosity. They represent our refusal to accept ignorance as a permanent condition. They reflect the desire to understand not only where we are, but what the universe truly is, and how it came to be the way it is. As we stand at the frontier of knowledge, one truth becomes increasingly clear. We are living through a unique moment in history. Never before have human beings possessed such powerful tools for investigating the cosmos. Never before have we had access to such extraordinary quantities of data. Never before have we been so aware of both our knowledge and our ignorance at the same time. The universe remains vast. It remains mysterious. It remains filled with questions that challenge our assumptions and expand our imagination. Yet with every observation, every experiment, and every generation of explorers, we move a little closer to understanding the grand structure of reality. And perhaps that is the most beautiful aspect of this entire journey. The cosmos does not reveal its secrets all at once. It invites us to search for them patiently, thoughtfully, and with a sense of wonder that never fades. If you enjoyed this exploration, be sure to like the video, subscribe so you don't miss future journeys, and share this story with others who are fascinated by the universe. Your support helps Cosmos for Rest, and it truly helps us keep going. Now, rest peacefully, and let the universe continue its quiet conversation with your imagination.